In digital signal processing, we often want to display the magnitude spectrum, so the absolute value of the discrete Fourier transform of the signal that we are analyzing. And today I'll show you exactly how to do it using the Python's Matplotlib library and to display such plot with various use cases, various scenarios. So let's go with the tutorial. If you're here just for the source code, the link is in the description below. But if you want to really master this method, I encourage you to watch this tutorial in full. So let's go. Okay, so the first thing I need to do is I want to create a virtual environment. So I'm going Python -m venv, and this has just created a virtual environment. Perfect, and now I can activate it. So I'm using PowerShell. So I'm using the PS1 script. Perfect, as you can see, it's activated. And now I can check that it's activated by asking where's the Python package manager. As you can see, it's in this particular directory. So now we can go ahead and install some packages. So we can install them into the virtual environment, not to pollute the global namespace. So what we need Matplotlib, we need NumPy, we need pathlib, and we need soundfile, and we'll need librosa. And as you can see, now the Python package manager installs all these dependencies locally. Okay, once it's done installing, we can go on with the tutorial. So we'll create a file called plot magnitude spectrum pi. Okay, and we can open it. So what you can see here, I have here a data sample from the Libri speech database. I have linked to it in the description below. But what we can do is we can use it to read it simply and then to display its magnitude spectrum. So for this, I use the soundfile library. So we have signal sample rate, and we'll do import soundfile SSF. And here we go, SF read, and here use the path from the Matplolib library. So from Matplolib import path, and here go path to current directory when the script is running at, and to the data folder. And then what I need is I need to simply copy this name, rename, copy name, and I paste it here, and we have our flag. And all I do, I'll just print what's the sampling rate of this file. Okay, and we need to create our boilerplate main, so that this function gets executed once we call it from the command line. And let's do just that. So we'll go Python -m plot magnitude spectrum. I can call it as a module. Okay, perfect. So it read my file and it says it's 16,000 hertz. Okay, so what we first need to do, right? We need to calculate the magnitude spectrum. And for this, we'll use the NumPy library. So we'll import NumPy as NP. And now we go, the magnitude spectrum is numpy.fft.rfft. So we're calculating the Fast Fourier transform of a real valued signal. And here we pass in the signal. But the thing is that we want to have a magnitude spectrum, so we need to take the absolute value, because the discrete Fourier transform is complex valued, so we need to take the absolute value to have the magnitude. But this is not all, right? Because we cannot just plot the magnitude spectrum on its own. It would be rather meaningless. So what we need to do, we also need to get the frequencies in hertz that this spectrum represent, especially that we have, this is a sample speech signal. So we'll go numpy.fft dot rFFT-frec, and here we go, signal shape 0. So we're passing the length of our signal, which is the length of the entire discrete Fourier transform, and then we pass in the time step. So here it may be confusing what are the lengths of these signals. So maybe let's print them out. So we have print magnitude spectrum shape 0, and we'll also print the frequencies shape. And we can also maybe print the signal shape. And let's run it. Okay, so as you can see, the magnitude spectrum is half the length of our signal, and that is because the real valued discrete Fourier transform is always symmetric, right, with respect to the Nyquist frequency. So this function already returns us half. This function already returns us half of the spectrum because we don't need actually the other half, and that's how I prefer to display it. And then this function rFFT-frec returns the frequencies corresponding to only half of the spectrum. Okay, once we have these, we can already write our plotting function. So we can go plot spectrum, and we'll pass in frequencies, and we'll pass in the magnitude spectrum. That's what we need. Okay, so let's create an appropriate function. Okay. And what we need to do here. So we'll need to, of course, create a figure, right? And I always like to pass here some constant fixed size. So the size of this figure will be 12.6. And we need to import the pyplot. So we go import matplotlib pyplot as plt. And now we can, what we of course can do is we of course go plt plot frequencies magnitude spectrum. And what I like to do, I like to pass in the color. So WolfSound color is EF7600. Okay, and pass in the color, and to display this figure, we need to call plt show. Okay, and we got our magnitude spectrum. Okay, nice. This is all linear scale. And here, as you can see or can guess, we have the frequencies, right, to 8,000 hertz because the sampling rate is 16,000 hertz. And we have some magnitude value, which is, in the frequency domain, we are mostly interested in the relative values of these particular frequencies. So relative magnitudes of the DFT. So let's start to first beautify our signal, because that's really important to have clear view what we have here. So let's add in labels. Let's add in the axis. Let's remove this ugly frame. Let's enlarge the font. Let's do all of this. So first, let's define the proper limits of our plot. So we want to plot from frequencies, from the first frequency simply to the last one, and we're not interested in displaying this white space around the spectrum, which also gives a false feeling because spectrum is digital spectrum is infinite, right? It repeats every sample rate. So it would give kind of a false feeling to have this white space around. Okay, then now we can add nice labels. So the X label is frequency in hertz, and the Y label is the magnitude, right? And then what was nice to draw, in my opinion, is to draw this x-axis. So let me just show you what I mean. So it's h lines, horizontal lines, and then we say, okay, at 0 from the limit to the end, draw a black line. Okay, let's see how it looks now. Okay, that's what we got. We got this black line here, and you know, these offsets are removed, and we have nice labels, but these labels are kind of small. So what we can do, we can here execute plte rc params and go update, and we can pass in font size. And it will become clear soon why I'm doing this globally for this whole script. Okay, let's think what is remaining. Okay, so here you see that the labels got way larger and are way more readable. So let's finally remove this ugly frame. So we go here and we go plt.gca, which removes the returns the axis object, and we go x spines top, and we call set visible false, and I'll do the same for the right and for the bottom. Okay, nice. You can see that we don't have this ugly frame here anymore. Okay, and of course, if you want to turn off the displaying of frequency or the magnitude, you can do so as well with specifying x6, but we don't want to do it here. And the last thing that's remaining for this part is that we want to save it, right? So let's maybe define additional function that we'll call the plot spectrum and save, and it will have, you know, exactly the same arguments with one additional one, which will be called output path, and this will be path object, and this will simply call plot spectrum. You have frequencies, magnitude spectrum, and then we'll go make directory. Of course, here I want to call parent. We want to make sure that the output directory exists. So we call, but if it exists, it's okay. And also we wanted to create the parents. And then finally we call multi-save figure, and we say, you know, the output path. And here we can pass in the parameters. So the parameters is the DPI is 300, and then the bbox inches, it's tight to really just contain the plot, not much white space outside. And what I also like to do is to set transparent to true, because then we don't have any background. Okay, and let's run this again. Okay, so this is our plot. And as you can see now, nothing was created because I haven't called this function. So, and let's define the output path as, again, this folder /image, and this is the output directory, and we can pass it here /spectrum.png. Okay, and let's run the script again. Perfect. The figure is displayed, and let's see what happens here. Okay, nothing is displayed, and that's why, because plt show closes the figure. So now we need to remove this, and now the figure is not closed and it gets properly exported to a file. One thing that's important to do here is also to call plt close, just in case we want to call plotting a few more times, because savefig doesn't close the figure, which means that it's open in the background, and there's a certain limit how many figures can be open still in the background. Okay, but what's wrong with this figure? So one thing that's wrong is that, you know, these magnitudes are very, very large, and they don't give us the full picture of what is happening, because our hearing is not linear in magnitude, but it's logarithmic in magnitude. So we often use the decibel scale to view magnitudes, and spectrum is no different. So let's now create another function which we'll call plot spectrum dB that plots the same thing but in decibels. So we have here plot spectrum dB, right? And this time we'll get not the magnitude spectrum, but we want to get a magnitude spectrum in dB. So for this, we go back to our main function, and we call plot spectrum dB, right? And we pass in again the frequencies, because the frequencies are exactly the same, but we want to pass in, magnitude spectrum in dB. So this will be something like, librosa amplitude to decibel. And here we pass in our magnitude spectrum. So, okay, that's like this. And we need to, of course, import librosa, right? Let me maybe lower this. And let's see, calculate our spectrum in dB. We pass it to plot spectrum dB. And well, now we got additional copies here. Okay, let me remove this one. Okay. And we go plt show again. And here we write dB. So let me call this function again. Okay, so now we got something like this, which is not very meaningful. That's because, like, what does it mean that, this is 40 and this is -20? It's hard to judge anything. So one thing for sure is that what we can do, we don't need this line anymore. We don't need this x-axis. But before we convert to decibels, it's more meaningful in the digital world to use decibels for scale. So we need to normalize the spectrum to the highest value. So this goes like this. Normalized magnitude spectrum. And we go magnitude spectrum divided by the absolute value, the highest value in the magnitude spectrum. So that's what normalization means. So the highest value in the magnitude spectrum will turn to 1, and the others will be relative to it. So now we can pass it here, and we pass it to our function. And let's try to run this. Okay, nice. And we got already something that's, you know, the top is always at 0, and we can see how the frequencies are relative to each other. So what is nice here is that we can, you know, limit the y-axis because we know that it's in dB. So we go plt y-lim, and we say minus 60. That's you know, often assumed as 0, but it's sufficient, you know, to have it like this. And then one additional touch that we can do, we can call plt grid, and now it will create a nice grid around the values that we are interested in. And here's the result. As you can see, we have a nice grid. We can compare the values, and it looks really, really nice. One thing that's not nice about this plot is that the frequency axis is linear. And, you know, in the audio world, our hearing is not linear in frequency. Our hearing is logarithmic. That's why we have a concept of an octave. So a sound 2 times higher in pitch by our perception. So we often want to display the frequency axis logarithmically. And that's exactly the purpose of our last function. So let me copy this again. And I'll call plot spectrum dB octaves. And let's see what changes here. It's this, instead of calling plot, we call this semi-log x. So the x-axis will be logarithmic, but the y-axis will still be linear in decibels. Oh, and that reminds me that we need to write here full scale, right? Because we have decibels full scale. And let's now, you know, plot it and see the result. I'll also comment this one because it doesn't need to be executed anymore. Okay, nice. So we got already something way more concrete, but it's still a little bit weird, right? So that's why we need to adjust it a little bit. So we need to change the limits. So as the limit, I'd like to take, you know, the frequency of 29 Hertz. And then, you know, the above limit can stay. So the last frequency available, in our case, it should be 8,000. Okay, this is way more meaningful, but now the labels are way off. And here's a trick that I learned from one of my friends, Simon Schwer. So he has, you know, like written out the frequencies, the octave frequencies as described by ISO. So I'll just copy and paste them here, and I believe you should do it too. So you should have them somewhere, either, you know, available in your own package or globally available. You can also extend it by other bands. So here are the ticks that we'll use. So, you know, these are the frequency ticks, and here are the labels of those ticks. And, you know, this is something you can reuse over and over again. So let me just call plt x ticks, and go x ticks and x tick labels. Okay, let's run this again. Okay, and this is now perfect. So of course we can maybe remove this lower label, but as you can see, we get nice lines, you know, everything is clearly visible. We get logarithmic frequency axis. We have decibels full scale. That's the true power of, you know, plotting the magnitude spectrum the right way. So I hope you enjoyed this video, and if you're curious how to do this, the link to the full source code is in the description. Feel free to copy, modify it, and so on. If you liked the video, please don't forget to hit the thumbs up, subscribe to the channel, and turn on notifications so that you get notified on the subsequent Python tutorials. Thank you so much. And if you'd like to create your own cross-platform audio applications or digital audio workstation plugins, I encourage you to check out Juice. Juice is an open source, cross-platform C++ application development framework that makes it easy to create audio software, as well as audio plugins and plugin hosts. You can write code once and build VST, AU, AUV3, AAX, and LV2 plugins on Windows, macOS, iOS, Android, and Linux, as well as embedded platforms. I've been successfully using Juice since 2018, both in my private and professional projects, so I'm delighted that they're sponsoring the video. I especially like how Juice makes it easy for beginners to jump right into creating audio plugins and applications without worrying about C++ quirks. Juice is used by the majority of the world's most important audio companies, but it is free for personal use, and there's affordable pricing available for companies just starting out. Apart from the framework itself, Juice has an amazing community of users gathered in the Juice forum, which is a great resource to learn audio programming on its own. To start using Juice now, go to juice.com, juce.com, download Juice, and follow their Getting Started guide. I have also put the link to it in the description. Thanks to Juice for sponsoring this video, and I wish you, dear viewer, much fun creating audio apps and plugins. Take care.